In today's video, we're going to look at partial fraction decomposition. Basically, finding the partial fraction decomposition of rational functions with linear and irreducible quadratic factors. So before I do this, let's refer back to when we did our polynomial unit. And we want to recall that when we added and subtracted fractions together. So let's say I want to add the fraction or subtract these two fractions together. First thing I had to do was find a common denominator, multiply each side by the common denominator, add the numerators together, and I'd end up with x plus 7 divided by x squared minus x minus 6. Okay, that was adding and subtracting fraction. Partial fraction decomposition goes in the other direction. I give you the answer, and your goal is to come up with the original two fractions that will add or subtract, that will add to equal this equation you have. So these original two fractions are what we call the partial fraction decomposition. So we're decomposing this fraction into two parts or into multiple parts, adding and subtracting. So decomposition of a rational function into partial fraction decomposition. First thing you want to do is you want to look at that rational function. If it is improper, you will need to divide using long division and divide the numerator into the denominator. Remember, it's improper if the degree of the numerator is larger than the degree of the denominator. So we'd go through our long division process, and we'll get a polynomial as our answer. So we'd have, divide to get your polynomial, plus, and then take the remainder, which I'm going to call n sub 1 of x, our new numerator, over our original denominator, which I'll just, to keep it likewise, term d sub 1 of x. And then that fraction that we get, that new fraction, is what we're going to do the fraction, the partial fraction decomposition process to. So what is the partial fraction decomposition process? First thing you have to do is you look at your denominator and you factor your denominator. So you have to completely factor the denominator into factors that are in the form that are linear or quadratic, as long as the quadratics are irreducible. So we're going to factor the denominator to factors of the form. For linear, that'd be the form of px plus q raised to some power, because you might have the same factor repeated. You might have repeating factors. And for quadratics, that's ax squared plus bx plus c. Again, we could just have one quadratic factor, or we could have repeated quadratic factors. And so, again, we're only going to use the quadratic factors as if it's a quadratic that will not be simplified, that cannot be factored, so it's irreducible. Okay, once you have your factors of your denominator, your next thing you're going to look at is we're going to look at our linear factors. So all the factors in the form of px plus q. So for each linear factor in the form of px plus q, we're going to have the partial fraction decomposition, and we're going to have as many linear factors we have, that's how many fractions we're going to make. So it will be a sum of n fractions because we have n linear factors. And what this will look like is you'll take your first linear factor, in this case px plus q, and write it in the denominator and make the numerator a constant, a, we'll call it a. Then the next factor is going to be some other constant, we'll call it b. And that next linear factor, in this case, it's the same one repeated twice. And you're going to repeat that until you have no more linear factors. So basically with linear factors, the numerator just becomes a constant. So notice the degree is one less than the degree given. For quadratic factors, for each quadratic factor of the form ax squared plus bx plus c, the partial fraction decomposition must include the sum of, again, m factors. So we have as many fractions, or as many fractions as we have factors. That's key to remember. So in this case, but this time, because my denominator is quadratic, my numerator is going to be linear. So I will not just write it as a constant a. Instead, my numerator is going to be ax plus b, because I'm always decrease the power by 1 to keep the fraction, how we work with these partial fractions. So my next quadratic factor is going to be under the term, the linear term cx plus d. And then we're just going to continue changing those coefficients, doing those next variables for those coefficients, until we get all the quadratic factors that we have. All right, so let's see how this works in actual practice, because that's the best way to learn partial fraction decomposition, is just to practice it. So in this example, number 1, I have a linear term on top and a quadratic term on bottom. So it is in proper form, so I don't have to do the long division. So my first step is to factor the denominator. So let's look at x squared minus 2x minus 15, and let's factor that. All right, so x squared minus 2x minus 15 factors to x plus 3 times x minus 5. Now I'm going to set it up. So my original equation, 5x minus 1 divided by x squared minus 2x minus 15 will equal to my first factor, which is x plus 3 over a over my first factor, and then b over my second factor of x minus 5. So that would be my partial fraction decomposition. Now my whole goal is to figure out what a and b is. So to do that, first thing I'm going to do is I need to figure out a and b. But I need to, in order to solve for a or b or anything like that, I need to get rid of the denominators, get rid of the fraction here. And so to do that, what I'm going to do is I'm going to multiply both sides of this equation here by our common denominator, which is going to be that x squared minus 2x minus 15. And when I do multiply the right-hand side by that, I'm pretty much multiplying each term by that factor. Okay, so everything gets multiplied by the denominator, the original denominator. Now, on the left-hand side, that cancels out and leaves me just the numerator. Okay, on the right-hand side, if I remember that x squared minus 2x minus 15 factors to x plus 3 times x minus 5, the x plus 3 and the x plus 3 in the fraction cancel each other out. And so that's left in the first term as a times x minus 5. And in my second term, it leaves me with b times x plus 3. Now, shortcut to this is that you can just multiply each numerator of the fraction by the left, by whatever factors you did not use in that fraction. And then I'm going to get rid of my parentheses by distributing the a and the b. Now let's group our like terms together. I'm only working on the right-hand side. So ax and bx are like terms, and then negative 5a, which is some constant, plus 3a, which is another constant, 3b, which is another constant, are like terms. Then to make it easier to see, I'm going to take the GCF of x out of this first term. So my coefficient of the x term is a plus b. The coefficient of the constant term, or the constant term, is negative 5a plus 3b. So what you want to do is you want to make a system of equations. This is my partial fraction decompositions in our systems unit. So I'm going to rewrite a system and say, okay, for the left-hand side of the equation, my coefficient of the x term is a plus b, and the left-hand side, the coefficient is 5, so we set those equal together. Same thing for our constant. On the right-hand side, our constant is 5a plus 3b, negative 5a plus 3b, and that is equal to my constant on my left-hand side, which is negative 1. Now you have a system of equation. Now you can solve this system using any technique that we've learned this unit, or any technique you know how to solve systems of equations. It really doesn't matter which choice you choose. I'm going to choose different options throughout so you can just see how you do it. So I'm going to use Kramer's rule. Since that's kind of fresh in my mind, we just did that. So my coefficient matrix is 1, 1, negative 5, 3. And when I find the determinant of that, I get 8. And then my a variable matrix, a determinant, would be 5, 1, negative 1, 3. And when I find that determinant, I get 16. And then my determinant of my variable b would be set up as follows. And then to find that determinant, I end up with 24. Okay, so my a variable is going to be equal to 16 divided by 8, which is 2. And my b variable is going to be equal to 24 divided by 8, which is equal to 3. So I'm going to go back to my original statement that I had wrote, my partial fraction decomposition written out, which was this statement here. And I'm going to replace my a with what I found it to equal, which is 2, and replace b with what I found it to equal to in this problem, which is 3. And so 2 divided by x plus 3 plus 3 divided by x minus 5 is my partial fraction decomposition of this problem. And you're done. All right, now I want you to try this next example. Okay, I want you to start by factoring your quadratic, your denominator. Okay, the factor of x squared minus 3x plus 2 is equal to x minus 1 times x minus 2. Now I'm going to set up for my partial fraction decomposition. So I want you to go ahead and find your partial fraction decomposition of this problem. Okay, setting it up, I get 3x minus 5 divided by x squared minus 3x plus 2 is equal to a over x minus 1 plus b over x minus 2. Now it's okay if you chose a over x minus 2 and b over x minus 1. The order you write these does not matter. Your same fractions will be the same. Just make sure you align your a with the right denominator when you go back. Okay, multiplying by our denominator to our every term, I end up with 3x minus 5 is equal to ax minus 2a plus bx minus b, combining like terms of ax and bx together, and combining my constant terms of negative 2a and a minus b. I end up that 3x minus 5 is equal to a plus b times x, and our constant term of negative 2a minus b. All right, so to set our system, we have a coefficient on our left-hand side equal to our coefficient on the right-hand side, so it gives us a plus b is equal to 3. And then our constant term on our right-hand side equal to our constant term on our left-hand side. So I get the equation negative 2a minus b is equal to negative 5. Okay, now we're going to solve this as system equation using any technique you know. I'm going to choose to do elimination this time because I have b and minus b already set up. So if I combine these two terms together, I end up with a negative a is equal to, the b's terms cancel out, and that gives me a negative 2. So dividing each side by negative 1, a must be 2. So if I found that a is equal to 2, I'm going to go back to my original equation, a plus b equals 3, replace a with 2, and I find that b has to be 1. So I now know that a is 2 and b is 1. So I'll go back to my setup of my partial fraction decomposition. And I'm going to replace the a with 2 and replace the b with 1. And you have now found the partial fraction decomposition of this rational function. For example 2, I had a complexity level in which I have a improper fraction. Notice the degree on top is larger than the degree on bottom. So if we have an improper fraction, we first must divide our polynomials using long division. So remember, when you do division, you must put in your placeholders. Please don't forget your placeholders. And I ask myself, what can I multiply x cubed by to get 2x to the 4th? And that would be simply 2x. And then I'm going to multiply each term on the outside by 2x. And then I'm going to subtract that from the given. So remember to distribute that negative. So I end up with positive 2x plus 0x minus 1. Since 2x squared is a smaller degree than x cubed, that is my division. So 2x squared minus 1 is my remainder. So now I can rewrite this original rational function as 2x plus the fraction 2x squared minus 1 over x cubed minus x. And now I'm only going to look at that fraction, 2x squared minus 1 over x cubed minus x, and do partial fraction decomposition with this fraction only. So remember, the first step to do fraction decomposition, we need to factor the denominator. So I know I have a GCF of x, so I can take x out. Then I have x squared minus 1, which is the difference of squares, which will factor to x minus 1 times x plus 1. So this has 3 factors, and they're all linear factors. So I would rewrite this as a over x, my first factor, plus, so I'd write this as a over x plus b over x minus 1 plus c over x plus 1. And then to get rid of my fractions, I'm going to multiply each side by the denominator of x cubed minus x. And so that a term, therefore, needs to be multiplied by x times x squared minus 1. And then the b term needs to be multiplied by x times x plus 1. And the c term needs to be multiplied by x times x minus 1. All right, simplifying down the right-hand side, I get ax squared plus a plus bx squared plus bx plus cx squared minus cx. And then putting like terms together, I have my ax squared plus bx squared plus cx squared for all my x squared terms. And then I have a plus bx and a minus cx for my x terms, and then a minus a. So writing these down, so I have my coefficients. I have a plus b plus c all times by x squared. And then I have b minus c times by x and a negative a as my constant. So combining, looking at the left and right hand side to make my system of equations. On the right hand side, the coefficient of x squared is a plus b plus c. And on the right hand side, the coefficient is 2. So I set those two equal to each other to make my first equation. And then the coefficient of x squared on the right hand side is b minus 2. But there's no x squared on the left hand side. So remember, because of placeholders, that means that our x squared is supposed to be, is actually a coefficient of 0 for our x term, sorry. Our x term has a coefficient of 0. So my second equation would be b minus c equals 0. And then my constant term on the right hand side is negative a. And I want to put that equal to the constant term on the left hand side, which is negative 1. So negative a equals negative 1. So I'm going to solve this by substitution method. So I have the equation negative a equals negative 1. So if I divide each side by negative 1, I get a equals 1. So I found my a. Then I'm going to go back to my first equation where I have an a term and substitute 1 in place of my a. Simplify that equation down. And I get b plus c is equal to 2. I'm sorry, b plus c is equal to 1. Then I have that b minus c is equal to 0. I'm going to switch over to elimination. You know, you can change these up if you want. And I end up with b is equal to 1/2. So now I know my b term, so I can go back to my second equation here where I have b minus c is equal to 0. And replace the b with 1/2 and solve this equation for c. And I end up that c must be equal to 1/2. Okay, so now we're ready to write our partial fraction decomposition of the original problem. So our original problem was 2x to the 4th minus 1 over x cubed minus x. So recall that we did long division to start with. So we need that polynomial from long division plus, and then what we did in the second half was the partial fraction decomposition of the remainder over the denominator. So that's what we're going to put here. So then we add our partial fraction decomposition part, and we're going to replace our a with 1, replace the b term with 1/2, and the c term with 1/2. We also have to do something extra with this. Notice that these last two fractions are compound fractions. We have a fraction over a fraction inside of a fraction. We never want to leave compound fractions in our final results. It's just messy. So I'm going to do the long way on the first fraction to show you how it works out, why the math works out, and then we'll do the shortcut way on the second one. So I need to take 1/2 divided by x minus 1, which I would write as a fraction, x minus 1 over 1. Now remember, when you divide by fractions, you flip and multiply the bottom fraction. And it just becomes 1 over 2 times x minus 1. Another way you can think about that is the denominator of the top moves down to the denominator of the big fraction. And so I could just rewrite the second one as 1 divided by 2 times x plus 1. So all 4 of these terms is my complete fraction decomposition of my original polynomial, my original rational function. So it's your turn. Try this one. First thing I want you to do long division and figure out what you get from long division, since this is an improper fraction. Okay, so doing long division, I will divide x squared plus x minus 2 into my numerator of 3x cubed plus 4x squared minus x plus 0. So I'm going to start by multiplying by 3x to every term and then subtracting that. I get x squared plus 5x. Now x squared is not less than the outside, so I got to do another another division. So I can go by 1. So I'm going to multiply everything on the outside by 1 and then subtract that. And I get 4x plus 2. So my doing the long division to this polynomial, this rational function, I can rewrite it as 3x plus 1, 4x plus 2, divided by x squared plus x minus 2. So let's look at our fraction here. I'm going to do partial fraction decomposition with this. So start by factoring the denominator. And the denominator will factor to x plus 2 times x minus 1. Now let's find that partial fraction decomposition of 4x plus 2 divided by x squared plus x minus 2. So we have one linear term, so a is over x plus 2. We have a second linear term, which is b is over x minus 1. Multiplying by our x squared minus x squared plus x minus 2 to each of our terms. We end up with a times x minus 1 plus b times x plus 2, which gives us 4x plus 2 is equal to ax plus minus a plus bx plus 2b. Combining our like terms together, we get that a plus b times x and our constant term of negative a plus 2b. And so to write our system of equation, our coefficient of our x on the right hand side is a plus b, and the left hand side is 4. So we set those equal, and I get a plus b equals 4. And our constant term on the right hand side is negative a plus 2b. Set that equal to our constant term on the left hand side, which is 2, to get the second equation of negative a plus 2b equals 2. Okay, we'll solve this system using any technique you want. I'm going to do the elimination method. And combining these two together, I get 3b is equal to 6, or b is equal to 2. And then I'm going to go back to my original equation of a plus b equals 4, replace b with 2, and solve for a. And I get that a is equal to 2. So go back to my fraction decomposition. And if I go back to my original fraction decomposition, I have my long division result I got. That's that x cubed plus 1. Now plus our fractions from fraction decomposition. And that would be our result. Okay, for our next example, we're going to do some of these that have repeating factors. So let's, again, this is proper fraction, so we need to factor our denominator. It factors to x squared times x squared plus 1, and x squared plus 1 is a quadratic that does not simplify down. So it's irreducible quadratic. Now notice that x squared is understood to be the linear factor x times by the linear factor of x. So it's x times x. So we'll break this up to actually 3 factors. We have the x factor, that linear factor, then the linear factor repeated, and then our quadratic factor. So we have 3 of these. So we have a over x, b over x squared, and cx plus d over x squared plus 1, because it's a quadratic base. So notice that x squared in our second term is a linear term repeated, so it still has just the linear term. Multiplying each side by our denominator of x to the 4th plus x squared. Multiplying through to get rid of our parentheses. We get ax cubed plus ax plus bx squared plus b plus cx cubed plus dx squared. And then putting like terms together on the right hand side, we have a plus c all to the x cubed term. And then for x squared terms, we have b plus d. And then we only have one linear term, ax, and we only have one constant term, plus b. So now we're going to combine these and write our system of equations. So our coefficient of x cubed on the left equal to the coefficient of x cubed on the right. So that's a plus c is equal to 3. And then our next equation would be coefficient of x squared. Well, on the right, it's b plus d. On the left, there's no x squared term, so it's going to be equal to 0. And then our coefficient of our x term on the right equal to our coefficient of x term on the left. So that means a is equal to negative 5. Oh, we already solved for a. And then our last one is our constant term on the right equal to our constant term on the left. So we get b is equal to 1. So we already know a and b. So I'll do this by substitution method since I already know 2 of the results. So we know a is negative 5 and we know b is equal to 1. So I can find my c by doing a plus c is equal to 3. Replace the a with -5. Solve for c and to get c is equal to 8. Then I can use the b plus d equals 0 equation, replace b with 1, and solve for d to get -1. So go back to my partial fraction decomposition, and I will copy this down, replacing the a with -5. So I'm going to replace the a with -5, the b with 1, the c with 8, and the d with -1. And there you go. There's my partial fraction decomposition of that original rational function. Okay, your turn. Try this one. Okay, factors of x squared plus 4 to the x power, that's square power is repeating. So our first factor is x squared plus 4. And our second factor is that x squared plus 4 repeating, so squared. So those are both quadratic terms. So on top, we're going to have ax plus b, and the second factor is going to have a top of cx plus d. Multiplying by our denominator to every term, I'm going to have my numerator times by x squared plus 4. And then on the next factor, it's just the whole denominator cancels out, and I'm left with just the numerator, cx plus d. So we're going to do the full method for these, multiply these two together. So that's going to give me ax cubed plus 4ax plus bx squared plus 4b, and then plus the cx plus d. And so combining like terms, my x cubed term is just a. So I have ax cubed plus my bx squared for my x term, my x squared term, plus 4a plus c for my x term, and my constant term would be 4b plus d. Now I'm ready to make my system of equations. My coefficient of the x cubed on the left-hand side is a, on the right-hand side is 1. Coefficient of the b squared term, the x squared term is b on the left and 1 on the right, or vice versa. And the coefficient of my x term is 4a plus c, and there's no coefficient of the x term on the right-hand side, so left-hand side, so I set that equal to 0. And my constant term's coefficient is 4b plus d, and again, there's no constant term on the left-hand side, so that's also set equal to 0. So I already know what my a is equal and my b is equal, so I can use substitution method to solve for c and d. So since a is equal to 1 and b is equal to 1, I can take my 4b plus d, replace b with 1, solve for d, and end up that d must be -4. And I could also do the 4a plus c equals 0 equation, replace the c with 1, and I get that c is equal to -4. So I'll go back to my partial fraction decomposition, replacing the results I found into this fraction. So I can replace, since a is 1 and b is 1, I have x plus 1 divided by x squared plus 4, and then -4x minus 4 divided by the quantity x squared plus 1 squared. And there's how you do fraction decomposition.